Okay, let's work this somewhat tricky example. This example is actually done in the textbook, so I recommend looking at that as well. So here in this problem we have some bucket of water. We're going to say it's mass little m. It's attached to this cylindrical winch of radius r and mass big M. And this mass is released, the bucket's released, and it falls into the well about 4 meters. We want to calculate how long it takes to do that fall. And the first step in doing this problem is we want to figure out what's the acceleration of this mass as it's falling. And then we can treat it like a normal motion problem. But for now we want to calculate the acceleration of that mass as it falls into the well. And so it's not going to be g. We know that. It's attached to this cylindrical winch. So it has to turn that winch as it's falling. And so first of all, this is falls into one of our no-slip conditions that we talked about in the lecture. So if that's the case, the acceleration of our object, and we'll call it the y acceleration because it's vertical motion, is equal to the radius times the angular acceleration of the winch. Now, since it's going to be moving downward, we'll take that as the negative direction. So we have to manually put a negative sign in here. Okay? So the angular acceleration then of that winch is the negative of the y acceleration of the object divided by the radius. Okay? Okay, now we also know the angular acceleration of this winch is caused by the torque that this mass is putting on the winch. Okay? And so angular acceleration is related to the torque. Well, it's the torque divided by the moment of inertia. Okay, torque is angular acceleration times moment of inertia, so the angular acceleration is torque divided by moment of inertia. Okay, now, what is the torque acting on this winch? Well, it's not mg. We'll clear that up here in a second. So, what's actually pulling on the winch as this is falling? Well, it's the tension in the rope. Okay? It's the tension in the rope that's actually pulling on the winch. And that tension is not equal to mg. And here's why. So let's look at our free body diagram for our little mass here. Okay? Well, mg, the gravity pulls down on our little mass, and tension pulls it up. And our acceleration, of course, we're assuming this is our positive direction for acceleration. So if that's the case, tension, we can see if we have an acceleration, tension isn't equal to mg. We'll come back to this in a minute here. So the torque acting on the winch is going to be the force applied times the radius. So the radius is r. The force is the tension. The moment of inertia, well, the moment of inertia, it's a cylindrical disk. It's 1/2 mr squared. Okay. Now, what is the tension? This is where we have to do a little bit of Newton's law funny work here to find the tension. Okay. So our Newton's second law says that the net force is mass times acceleration. Okay. So the net force acting on that mass is the mass times the y acceleration. Okay. Now what is our net force here? Well, since up is the positive direction, we have tension. Okay, that's one of the forces, minus mg. Okay, minus because mg is downward. Okay. Okay, so our tension then is mg we add this to both sides. It's mg plus the mass times the y acceleration. Okay? So that needs to go in here eventually for tension. Now, we have two expressions for angular acceleration. Angular acceleration is this, and angular acceleration is also this. So this, therefore, these two expressions are equal. Okay? So let's write that out then. Negative y acceleration divided by r is equal to this, which is r times the tension. The tension is this. So let's plug that in here for tension. R times mg plus mass times y acceleration divided by 1/2 mr squared. And since this is being recorded on video, you can always step back and look at this if you need to. I'm just going to erase this stuff. Okay, so there's our expression here. Now we want to solve for acceleration. That's how we're eventually going to solve this problem. So let's try to cancel out as much as we can here. This r cancels with one of these r's. This r is going to cancel with that r. And once we do a little bit of solving, a little bit of algebra to solve for the y acceleration, you find the y acceleration is negative mg divided by little m plus big M over 2. Okay? And now I am actually going to erase our little diagram here. Okay, so we plug in the values we're given in the problem. Little m is 2.5 kilograms. That goes in these two places. G is 9.8 meters per second squared. Big M is 3 kilograms. So you do that calculation, you get the number negative 6.13 meters per second squared. Okay? Now to calculate the time, we need to utilize one of our kinematic problems going back to chapter 2. And so recall there's this equation that says y final minus y initial is Vy initial times time plus 1/2 y acceleration times time squared. And let's go ahead and erase some of this stuff up here. Now what's our initial y velocity for our bucket? It's 0. Our bucket starts from rest. So this term is going to be 0. Now what is y final minus y initial? Well, here's our initial position, and here's our final position down here. So y final, if this is our height of 0, and this is our height of 4 meters, then y final minus y initial is the negative of our height. Okay? So if this is 0 and that's 4, 0 minus 4 is negative 4. So our height is 4 meters, so it's negative h. So solving for t then, t is then the square root, after doing the algebraic steps here, multiply both sides by 2, divide by y acceleration. It's negative 2h over the y acceleration. Okay, so h is 4, so this is then square root of negative 2 times 4 meters. Our y acceleration is negative 6.13. That goes in right here. And you do that calculation, you find that the time it takes to hit the bottom of the well is 1.14 seconds. So that's a tricky problem. It incorporates a lot of different things. It incorporates torque, Newton's laws, to figure out the tension in the line here. It incorporates our rotational dynamics. It also incorporates, calculating using kinematics, doing motion type problems. So that kind of includes a lot of different physics in it.